Okay, I had a lot of emails over the weekend about the radical chlorination. Um, Apparently, I didn't get to all of them. Sorry about that. I'm getting about 100 emails a day, and it's hard to stay on top of them, on top of doing everything else I'm doing right now. Obviously, having to email me and me having to respond to 100 emails is not the most ideal thing. But one of the things that I'd like to point out to you guys is there is an example lab report on Blackboard with a rubric that shows you basically what I want for each section, the format that I want it, okay? The MSDSs, where you guys just basically can find these compounds using a variety of sources. And the experimental procedure, which is straight out of Blackboard, the apparatus, and on the welcome email or the welcome video, I told you guys you could just, cut and paste the apparatus, or you could build them if you wanted to in ChemDraw. I strongly encourage the chemistry majors to get familiar with ChemDraw because it's a tool that I've been using since I was doing research as an undergraduate many years ago when it first came out. Your observations, where do you get your observations from? The videos, right? So we recorded the experiments. So observations will be from the experiments. There's one experiment that we didn't get a chance to record. So for that particular experiment, there will be no observations, but I'll tell you that when we get to that experiment. And the format. And so again, it's one of those things that, I mean, this is like, as an undergraduate student, when I was taking labs, this was gold to me. And so I had my first example lab report, because you know how it is, every professor wants something a little different, right? And so when I took analytical chemistry with my analytical professor, he gave us this. And I was just like, this is wonderful. And so when I would sit there and I would do my lab report, I would have this open in front of me so that there was no confusion as to what it was exactly that he wanted. And I talked about this in the video, the introduction video. And I know that sometimes it's difficult to find melting points and boiling points, but they're out there, and I wouldn't have asked you guys to get them if they're not out there. Like this one is very difficult to find for the procedure we're doing today. And so I included the melting point. Okay, and I'm going to mention to you guys as we go through this that the only thing you need to include for the product is the melting point and the molar mass, because you won't be able to find the density of this very easily. You won't be able to find, well, that's really it for this compound here. And so again, the lab report example is your Bible when you're writing your lab report. And I took a cursory look at them yesterday, and for the most part, the ones I saw yesterday were pretty good. But it was early in the day, and I didn't look after that because it's Sunday. So again, this is what I want you guys to use. Okay, and I gave this to you guys so there would be no confusion, and that you would know exactly what it is I want. And this is what my TAs use as their rubric. So, and then I add stuff for what I want points deducted for, and I send that to them, okay, for your specific lab for that week, because they're all different, right? And so again, it's and every piece of data that you get, you need to comment on. If I give you a melting point, you need to talk about your melting point. Okay. If I give you an actual yield, you need to calculate percent yield and this, that, and the other. If you get an IR, like we're going to talk about in a little bit, and an NMR, you need to comment on what I tell you to comment on. Okay. And if you don't know how to do IR and NMR, I've got the actual, it's long, because it's my actual, what is it called? Lecture that I give in Organic 1. It's 3 hours because it's NMR, IR, and mass spec. So again, where is it? Oh, I thought I put it on here. Did I not put it on here? I thought it was on here. Oh, I thought I put it on here. I thought I put it on here. Damn it. No, this is not it. Anyways, I'll post it from last semester, but it's 3 hours and it's not that bad. And then also too, I have this correlation table. So this is in your book. And last semester, Dr. Aguilar provided you with one, and mine's the same way. It's just, our format's different, but it's the same information, right? And so again, if, you look at a phenolic proton versus a carboxylic proton versus an aldehyde proton versus a vinylic, versus an allylic proton. And all this stuff is there. Also too, and we're going to talk about this later, I've actually broken down the different carbonyl stretches for you. And so we're going to have 2 different carbonyls for this lab. And so you're going to have to identify which carbonyl peak is which one, because there's 2. Okay. And so again, it's commenting on your data that's important. Okay. And so you will get points deducted if you don't comment on all your data. Okay. And that's, it's a lab report. I'm not certain what else I can give you. And if you want me to give you more stuff, just let me know. Now is the time to let me know. But aside from just telling you guys what you have and telling you what to write, I don't know what else to do. Okay. All right. So we're going to be doing the Diels-Alder reaction, which is quite possibly the most studied reaction of all of organic chemistry. For those of you guys that are in the lab, you guys started talking about the class, you guys are talking about molecular orbital theory. Molecular orbital theory was actually born out of observations that were done watching Diels-Alder reactions. And so I'm not going to go into the MO theory of this, but I will talk about it, okay, in terms of its generality, okay? And so for a Diels-Alder reaction, you have 2 species. You have a diene that's going to act as my nucleophile. Then you're going to have a dienophile that's going to act as my electrophile, which is kind of weird because we think about this in terms of electrophilicity and nucleophilicity. We don't typically think of species with pi bonds to be electrophilic, at least not at the beginning of the reaction. But this is what we see here, okay? We've got partial positive charges, okay, at these 2 carbons because that pi bond is polarizable. And so that pi bond is pulling electron density away. And because it is polarizable and it is pulling electron density away, okay, my pi bonds have partial negative charges. So this is what we call a perion cyclic reaction. It's an addition reaction. We can classify it in a whole bunch of different ways. But the general reaction is that we go and we take our pi bond and we form a sigma bond. We break this pi bond and form another sigma bond. And then we take this pi bond and we form another pi bond. And the resulting species is going to be cyclohexene. And so with the Diels-Alder reaction, you're always going to form a cyclohexene derivative. Here, here, and here. So if you think about it in terms of delta H's, this reaction has a very large negative delta H because of what? Because we break 1, 2, 3 pi bonds that have an energy of about 68 kcals each. Oops. And then we form, okay, 2 sigmas and 1 pi, and the sigma bonds have an energy of about 88 kcals each. And so this is a highly, highly exothermic reaction, but it does require heat because my diene needs to be in this high energy conformer. Okay, and so the conformation of this is, have you guys done this in class yet, y'all? Have you guys lectured? Yes. And so what is the name of this high energy conformer? What is the conformational name? S-cis, right, S-cis. And so basically what we get is we'll start off with 1,3 butadiene, which is this guy here, in the so-called S-trans position or conformation. We add heat to allow it to overcome the barrier to rotation. And then we get the so-called S cis conformer, okay? And so have you guys had this exam yet? Have you guys had this exam yet? No. Yes, no, yes, no, Friday. Okay, so some of you have, some of you haven't. Okay, I'm talking about people that are in this semester. So I'm just gonna go ahead and do a real quick recap, okay, of groups that help activate and groups that help deactivate either the diene and the dienophile. And they come in two different flavors. Electron donating groups do what we call activate the diene, and as it would be expected, they would do what? They would deactivate the dienophile. And you think about it, okay, my dienophile is an electrophile, so it needs to be electron poor, okay? My diene is a nucleophile, so it needs to be electron rich. And when I have electron donating groups, okay, I'm adding electron density to my nucleophile, okay? We rank them in orders of their donating ability, okay? Amino groups are the strongest. So R can be an alkyl group, or R can equal to hydrogen, it doesn't matter, okay? The lone pair of electrons on the nitrogen atom can help to donate, okay? Followed by hydroxy, followed by an ester, followed by an amide, or, now this is important, any of these species here where the connection, okay, is directly on the heteroatom to the diene. In other words, it would be like, I'll show you an example. And then lastly, would be an alkyl group, okay? These first few donate via resonance. And the alkyl group donates by what? Inductive. We know that alkyl groups contain carbons. We know that carbons are electropositive. And so we know that electropositive atoms donate electron density, okay? And so again, let's take an example, okay? I'll show you what I mean here. So let's take this diene and let's add an ester group here, okay? So we know that we have a lone pair of electrons, and we also know that this lone pair of electrons can resonate either way, either towards the carbonyl carbon or towards my diene, okay? But we're not gonna resonate towards the carbonyl because that doesn't prove my point. And so we're not even gonna bother with that, but we know that I can do what? I can move my pi bonds this way, give me a partial negative charge here. I'm sorry, an actual negative charge there. Positive charge here, okay? And it's like so. I can continue to move this negative charge here, continue to move this pi bond down here. And then I have this resonance form. And so what I see is by putting this oxygen atom directly attached. Now again, if I flip over and I attach it by the carbonyl by the acyl group, the CH3 group, okay, it actually changes. It actually changes. So it's very important how it's connected, okay? I draw the resonance hybrid. It's going to look like something like this. Again, I know I'm excluding one of the resonance hybrids because it's not important to the demonstration, okay? Oops, shoot. I don't know why I'm having such issues. Okay, it would look something like this. And what I would see is I would start to develop partial negative charges within the structure, and these partial negative charges increases electron density, ergo increases nucleophilicity, okay? And again, we have groups that, questions about this, for those of you that are going to be tested over this soon. No? I'm assuming that all of you guys have been shown this in class or something like this in class. Then we have electron withdrawing groups. Okay, so they decrease electron density in a dienophile. Okay, making it more electrophilic. Okay, and so again, oops, sorry about that, guys. And so again, they come in a bunch of different flavors. We have what is known as an amino group. Ammonium, I'm sorry. Okay. Followed by nitro, followed by, I always forget about this one, sulfonic acid group, followed by a nitrile group, followed by, now this is important too, oops, a carbonyl group, where now the carbonyl is directly attached. So the carbonyl is attached here to the diene. I'm sorry, to the dienophile. Okay, and then of course the last one would be, okay, a halogen. Okay. So this first one is basically electrostatic interactions. If I have my dienophile and I have this ammonium group here, the electron density is going to be pulled towards this positive charge. Okay, so it's not resonance, it's not inductive effect. It's basically an electrostatic interaction between the nitrogen that's positively charged and the electrons that are in the bond. Okay, over here, these are resonance. Oops. Okay, and of course the halogen is inductive. And so again, we can look at the resonance forms. So say I want to put a nitro group here, and I want to do resonance with the nitro group, and what I'm going to find right off the bat, that a lot of you guys will want to put a lone pair of electrons on this nitro group, and then what you're going to do is you're going to realize, well, I can't resonate. The only thing I can see is I can go this direction. And that's not correct, because why? You have to actually draw out the entire structure of the nitro group to see how to resonate here. Okay, you have to draw it out to where you're showing how the nitrogen has 4 bonds and is positively charged, and the corresponding oxygens. And again, I know that I can resonate between those 2 oxygen atoms. I know that, but it doesn't show how this makes my dienophile more electrophilic. And so what I can do is I can just take this pi bond and resonate this way, push this pi bond here. I get a partial charge here. I'm sorry, an actual charge there. And then when I draw out my resonance hybrid for the 2 structures that I drew, I get a partial positive charge here, partial positive here, partial negative here, partial negative here. Okay, and so again, the dienophile is acting as an electrophile. If I can pull electron density out of the carbons that are doing the reacting, okay, that makes it more electrophilic, and it also makes it more attracted towards the nucleophile. Okay, all right, questions about that? Any questions? All right, let's take a look at what you guys are going to be doing this week. Okay, you're going to be taking, well, you're not going to, you're going to be watching a video because of stupid COVID. It's actually a really cool lab. Okay, we're going to be taking this diene, which has this name. Okay, it's a alcohol. We're going to be reacting it with maleic anhydride, which is probably one of the best electrophiles out there. Okay, and we're going to be making this compound here. And if you look at this name right here, okay, that's long. That's long. In your lab report, and I told the TAs this, because nobody wants to see this word cut and paste 100 times in your lab report. You may refer to this species right here as the Diels-Alder product or DA product. Okay, you can just call this DA product. Okay, because like I said, nobody wants to read this word 1,000 times. Okay, all right, so let's look at the mechanism. We're going to start, well, we're going to start with my my alcohol. We had to heat this reaction. This reaction takes place in the presence of toluene. Toluene is an organic solvent, okay, and it's very nonpolar. Okay, toluene has this structure here. Okay, it's a benzene ring with a methyl group. So methylbenzene or toluene is its common name. Okay, we're going to rotate it to where we get the so-called the S-cis conformer. Okay. Then we're going to react it in the presence of maleic anhydride. It looks like this. So this first part is just a traditional Diels-Alder reaction that you would expect to see. After this, it's going to get a little funky. Okay. We're going to get this right here. There's my cyclohexene core. What we notice is that all of these substituents are coming off. Okay, all of these substituents are coming off in these so-called all cis. It's probably easier just to draw this in ChemDraw first as like just a regular line form and then add the stereochemistry. Okay, so just draw it normal and then go ahead and add in all your stereochemistry. Okay, so this is what we have right here. Okay, but if you notice, if we look at the product here, it doesn't look anything like what we have. Okay, we have a lactone, which is a cyclic ester rather. A cyclic ester is called a lactone. And I have the carboxylic acid group over here. Okay, over here, okay, I have this anhydride, which is this functional group here. And then I have this alcohol. Obviously, the reaction doesn't stop here. The rest of this is basically stuff that you're going to talk about after you finish going over aromatic chemistry. Okay, but what we do know with carbonyl chemistry, carbonyl compounds have this resonance form. And as a result of that, the carbonyl carbon is an electrophile, and it's a great electrophile. Okay, this is a great electrophile. We know that alcohols are nucleophiles from last semester. And so what we're going to see here is we're going to see nucleophilic attack of the oxygen atom. We're going to break this pi bond, and we're going to form another cyclic. So we're going to have a cyclization reaction here. I'm going to go ahead and drop the stereochemistry just to make it easier for me to draw. You guys must continue to write the stereochemistry. But again, if I was using ChemDraw, I would just be cutting and pasting like a crazy woman right now. So we have this new bond here. Okay. And the oxygen atom that was a carbonyl is now a negative charge. This tetrahedral intermediate species is going to form a carbonyl bond. Anytime you can reform the carbonyl bond, you do. Why? The carbonyl bond is actually very strong. If you look in your biological molecules, carbonyl chemistry, carbonyl bonds are ubiquitous, right? The very building blocks that makes you, your amino acids and your proteins and your enzymes, okay? They are formed by compounds that have a whole host of carbonyl bonds. Every amino acid, when it goes and it forms a peptide bond to form one of your proteins, there is a carbonyl bond. And the reason I'm going to guess nature chose that is because they are very strong. And so you can pretty much always guess, if you see something that's all over the place in nature, you can make the assumption that that is a strong bond. And so what we're going to do now is we're going to reform the carbonyl bond, but to do that, we have to kick off a leaving group. This entire moiety here is going to come off as a leaving group. Now, why not this? Why not this as a leaving group? Okay. It probably happens. Okay. And what you have to remember that every time we talk about these reactions, especially these intermediates, we're in equilibrium. Okay. And so the fact that this group doesn't necessarily come off. I just realized I wasn't sharing my video. Sorry. I was told to share my video. Apparently you guys find it comforting. I don't know how that's the case. Sorry about that, guys. Anyways, anytime you think that there's another pathway that a reaction can proceed in that makes chemical sense, you're probably right. Okay. But there are tricks that we can employ to push one reaction pathway, have it favored over another. And so that's the case here. Okay. And so as I reform this carbonyl, this leaves, okay, and it's going to come off as an acetate group. And then what we're going to have is we're going to have an intermolecular proton transfer that's going to form our final product, which is this guy here. And again, after you draw everything, just go ahead and make sure everything is all wedges as they're coming off. Okay, that's really ugly. Again, it's much easier to draw this in ChemDraw. So that's your final product. Okay, now here's the deal. Okay, again, every single one of these steps is an equilibrium. As soon as we form this is pretty polar. Okay, this reaction is taking place in toluene. And so as soon as this is formed, it precipitates out. Okay, and you guys remember when we were talking about Le Chatelier's principle back in Gen Chem 2, right? And we said that we can push the equilibrium towards the product side by doing what, right? Removing product, okay? Even though it's still in the reaction flask, when it's no longer part of the homogeneous mixture, in other words, basically these two species here are soluble in toluene. And even though it doesn't seem like this ionic intermediate and this ionic intermediate aren't, they really aren't. But remember, they're intermediate species, so they last for maybe a femtosecond. You know, it's not like I can isolate either one of these intermediate species. Okay. And so what we see is as this precipitates out, okay, even if I do go backwards, right, and I kick off this group here, from time to time, I will go forward and I will continue to go forward. Once I reach this point and this precipitates out a solution, the reverse reaction is no longer possible. Does that make sense? In other words, I can no longer go in the reverse reaction. Okay, and so now I'm making product. And again, that just drives everything towards completion. It just drives everything towards completion. All right. All right. Questions about this? Questions about this? Okay.
A quick question about the heat, when it's added, that would that also just be one forward arrow as opposed to equilibrium between the S-cis?
Well, I mean, yeah, I mean, there is an equilibrium here, right? I mean, for the most part, this entire reaction's in equilibrium, but this is just more like between two conformers. But once the diene attacks the dienophyte, it can no longer go back.
Okay.
Yeah. But yeah, I mean, I was actually just talking about this today in my Organic 1 class. And when we talk about conformational analysis, I mean, theoretically, all of my conformers are in equilibrium with each other, right? Right?
Yes.
Okay. All righty. So watch the video. Your midterm's coming up in a few weeks. And so if you want to know what's going to be on the midterm, stuff I talk about in lecture, stuff I talk about in the videos for the experiments, stuff I expect you to know, like calculations and whatnot. Okay. And so that's what you need to be focusing on. Okay. That's what you need to be focusing on. Okay. So as far as the data analysis, everybody's melting points, I already uploaded the data this morning, so everybody's melting points are pretty close. Okay. If you look again on Blackboard, everybody's been given hold on, data. Okay, so student data. Okay, and so if you look here, you have your actual yield, of course, but you also have an NMR assignment. And so this is from obviously a pre-COVID semester where I just stole a bunch of students' NMRs. Okay, and so these are the NMRs that you're going to be analyzing. Okay, obviously this is a carboxylic acid peak because it's so far downfield. Okay, and then you have all of this other stuff. Okay, this is not the NMR that we showed you in Organic 1, right? This is not what we showed you. If we would have showed you something like this in Organic 1, I don't know what you guys would have done. Okay, there's going to be impurities in here because why? This is student data. Okay, and then some of them might not look that great for whatever reason. Okay, but you can still kind of figure out where everything is based on what I'm getting ready to tell you. Okay, something else that you never saw in Organic 1, solvent peaks. I'm going to talk about solvent peaks in a little bit, but if I zoom in here, it's kind of hard to see, but this is a pentet right here. This is not part of your product. This is the NMR solvent. Okay, the first lab, the spectroscopy lab, you were supposed to run your own NMRs, but again, it's not an issue right now because we can't go into the lab. And so you look here, there's two numbers, there's A6 and there's AA. AA was the section number. Okay, what you're going to be focusing on is A6. So if you're B2, then you go find B2 and so on and so forth. And unfortunately, I don't know, these are not in any order. You can't, oh, there it is. So there's B2. Okay, and so, and this, that, and the other. Okay, so real NMRs. Real NMRs. So how do we do real NMRs in the real world? Well, we have to run our NMR in a solvent. Okay, so you have an NMR tube, which looks like a very skinny test tube. It's actually about the same length as this, as my Apple Pencil, but the diameter is probably half the size. Okay, you have some solvent, a sample. Okay, but it's solid, which means it's not homogeneous. Okay, and so what we do is we use NMR solvent to make your compound dissolve, and then that way when we expose it to the magnetic field, okay, it has more degrees of freedom. In other words, it can respond to the external magnetic field. Okay, and then what we get is we get a nice homogeneous solution with your product hopefully nice and dissolved in here. Now, what are we looking at? We're looking at proton NMR. Okay, and so every proton that's on our compound, we want to be able to see, right? We want to be able to see each one of those protons. If I were to take an NMR solvent, oops, like DMSO, okay, the solvent to solute ratio here, in other words, your product being the solute, is very, very high, right? If I were to just use a regular solvent, you wouldn't see your product. Because why? Okay, because the hydrogens from your solvent would blind out the hydrogens from your compound. The analogy I always use is if I were to take a flashlight up to the sun and I were to turn it on, would you be able to see me? No, you wouldn't be able to. And so what we use is we use deuterated. Deuterated solvents. And so we know that H1 is hydrogen, and we know that H2 is what? The deuterium atom, okay? So the hydrogen's the only atom whose isotopes have their own atomic symbol. And so what we do is we replace the hydrogen atoms with deuterium atoms. We replace the hydrogen atoms with the deuterium atoms. But because it's a teaching lab, only about 99.9% of what we're going to see is deuterated. Some of it is not deuterated. Sometimes these deuterium atoms get exchanged. Okay, so from time to time, you will have this case. From time to time, you will have this. And this proton shows up, right? NMR doesn't know between solvent, NMR doesn't know between impurities, NMR doesn't know between products. NMR looks at proton signals and that's it, and it processes all those proton signals, okay? And in addition to that, it might be wet, so there might be a little bit of water here. And so sometimes we're gonna see a water peak. And it's difficult to keep the water out of the solvent because, you know, you're opening up the lid, it's San Antonio, it's humid, water's just gonna get in the solvent, and you can see it can hydrogen bond with the DMSO quite nicely, okay? And so in your NMR, and I'm always gonna tell you what your solvent was, okay? Your solvent that we're gonna be using for the Diels-Alder reaction is DMSO, okay? Which means that you're gonna have a pentet, a DMSO pentet at 2.5, okay? And then you're gonna have a water singlet at 3.3, okay? And if you go and you look at the NMR, you can see, because we tell the NMR what solvent we're running in, so it knows to look for those peaks, okay? Now, if you look at the water, okay, it's kind of overlapping. It's kind of right here. And if you look at the DMSO, okay? And so the problem with overlapping peaks is it throws off your integrals. It throws off your integral. And so if I'm doing an integral, how many of you guys know what an integral is? Like the actual mathematical definition of the integral. Okay. Summation under the curve. That's exactly right. Okay. It is the sum of the area under the curve. And if I have three hydrogens, if I have three hydrogens, they're going to have a signal and we integrate, okay? And then the NMR pops out 3H, right? And so I might have a signal that looks like this, for example, okay? But if I have something else overlapping with this, and even though it's not there in a whole lot of amount, I may have, now remember, these are relative values. So even though it might have one hydrogen, it's not going to have a full hydrogen because it's not there in a very large amount. So I might have a 0.6. So what you're going to get then for this peak is you're going to have 3.6. 3.6. Now, you guys aren't looking at this like you have no idea what you have. You guys know what you have. And so you know what this peak is supposed to be. You know if it's supposed to be a hydrogen 2 hydrogens, 3 hydrogens, okay? And so when you go and you look at this, we're going to take our compound, and we're going to look and see where on our NMR everything is going to show. I don't know why I just erased all those hydrogens. Oh, and I forgot, there's another solvent here that we're going to be using for our more nonpolar compounds, and that's CdCl3. CdCl3 because of the 3 chlorine atoms, it's much more de-shielded. Okay, it's all the way down there because of the inductive effect of the chlorine atoms. And water has a chemical shift of 1.5 in CdCl3. But again, okay, all of these will be mentioned when I send out the data or when I talk about it in class. Okay, so pay attention to that because you will be held responsible for knowing that the solvent peaks and the water peaks will be present in the NMR. All right, so this is what we have here. But this is a hot mess. This is a hot damn mess. And oh, for some reason I didn't. Well, somewhere down here is going to be, okay, my carboxylic acid. Let me go back over to an actual NMR. I don't know why this isn't on here. It's going to be here. You see how it's 0.7? Okay, so I'll make it 0.7. Obviously, you know, this is your carboxylic acid, so I'm going to call this HA. HA. Why is it low? Because of exchange. Okay, that proton can leave and come back because it's acidic. And so as a result of that, when the computer is doing its integration to figure out how many protons are responsible for that signal, sometimes there's not a proton on that carbon because it can come and go back. Okay, so there's that. Let's go back over here. Okay, this is junk, so let's ignore that. How do you know it's junk? Because I told you it's junk. That's how you know. These are my so-called allylic. I'm sorry, vanillic. Why did I say that? These are my so-called vanillic protons. Now, again, we don't have enough information with this spectra, okay, to say which is which. We'd have to do another experiment. So simply label these as being the same. Simply label these as being the same. Now, we have these other 2 peaks down here. Okay, do we have any protons that we would expect to be as far downfield as 4 or 4.5? Let's look at our protons. I have this one here. I have this one here. I have these 3 here. Let me not use green again. I have this one here. This one we've already identified. I have this one here. And then I have these 2. I'll use purple. I'll use pink. I have these 2 here. So, answering with the color, which protons would you expect to be that far downfield? So we've already identified the purple ones, Rosie, right? We already said that those were yeah, the pink ones. And Jenny hit the nail on the head. Those are what we refer to as diastereotopic, which means what? We lack free rotation. And so one of these protons, its relative position to this oxygen atom is going to be different. So one of these protons is going to be further downfield than the other proton. Again, we lack the ability to judge which is which. So I'm simply going to label these D and E and here. Okay. Now, the rest of these are a little crazy, right? The rest of these are a little crazy. So let's just go ahead and let's figure out, can I figure out off the top of my head where this CH3 group is based on what I have? Now give me a chemical shift. The most upfield, yeah. And you can see that it's a doublet, right? So this is the CH3. So I'm going to go ahead and I'm going to label these F. And I'm going to label these HF, okay? And now I have all of these down here. So this is what I call the cluster, you know what. All right, so again, going back to my correlation table. Okay, what kind of proton is this? What kind of proton is the orange proton? It falls under this range here. It's allylic. Okay, and according to my correlation table, it could be 1.8 to 2.2. Same thing with this other green one down here. Okay, it's also allylic. Okay, 1.8 to 2.2. This one right here, this dark green one, which I guess I just used dark green, is what? It's a carbonyl. It's what we call an alpha proton. If I'm in this position here, I'm said to be in the alpha position. Oh, sorry, guys. So you guys didn't see shit, right? All right, so starting over. Okay. This proton here is what we call allylic. That's its chemical shift here. Okay. This proton here is also an allylic proton. Oops. This proton here is also an allylic proton. So we would expect a similar chemical shift. Then we have this alpha proton right here. And again, according to my correlation table, it looks like this. Okay, the alpha protons are right, oops, that's the IR crap. The alpha protons are right here, and we can expect those to be anywhere between 2 and 3 ppm. So this one would be between 2 and 3 ppm. Same thing over here. Between 2 and 3 ppm. You would expect this green proton down here to be what? A triplet. You would expect this proton here to also be a triplet. You would expect this proton here to be what? A triplet. Oh, I already did that one. You would expect this proton, however, to be what? Okay, 1, 2, 3, 4, 5 neighbors. You would expect this proton right here to have what? 1, 2, 3, a quartet. Okay, and so again, now we've kind of figured out what everything should be. You're like, yeah, it's crystal clear for me right now, isn't it? Right? Crystal clear. Okay, this is where I'm going to help you out a little bit. Okay, this is where I'm going to help you out because frankly, it's very difficult to know which is which. Where did I live off of? F, G, HG, HG. Okay. The only reason I know this is because I've looked at a bunch of NMRs. That's how I know that. Okay. The next one would be my pentet. So the green hydrogen here. Okay. I'm just going to call it HI because I don't want to do HH. So this would be HI. And now we have the 2 triplets left over. So the only ones I haven't identified yet is this one and this one. And so again, we really don't have enough information to answer this question with the experimental data that I gave you. So I'm just going to go ahead and give it to you. What did I leave off? HIJ. So we're going to call this one HJ. Okay. And then this last one, HK, is HK. Okay. So there should be absolutely no confusion as to what you need to label on your NMR peak. Okay? Should be no confusion whatsoever. The only reason I'm doing this for you guys is because I will stipulate to the fact that this is a relatively complicated structure. What do you do with your NMR data that I gave you, that I assigned you? You compare your NMR data to this NMR. Are they the same? When you go and you make something in the lab, that's what you do. If you have a reference NMR, okay, if I'm trying to make compound Z and I have an NMR of compound Z, I'm going to run an NMR on what I made in the lab, and I'm going to compare it to the so-called literature or reference data. And that's what you do. The NMR that I have matches the NMR that Professor Doherty provided. Okay, so I know it's the same. Okay, impurities. Where are you going to get impurities? Okay, some of you guys are going to have a little bit of leftover toluene. Okay, this person actually did a really good job. There's not that much toluene there, but it's there. Okay, so make sure you label your impurities. Okay, also too, the methyl group for toluene is right here. So again, this person did a pretty good job. So that's an itty bitty toluene peak. So they did a really good job getting rid of all the toluene. Okay. The other thing that you're going to comment on, of course, is your is your IR. And so again, let's draw the structure real quick because I know I'm going over just a little bit. Don't worry, guys. This is the last long lecture. It's almost like at the beginning of the semester, it like totally sucks in terms of the amount of information, and then it really does go down from there. Okay, so I'm not going to go over what it is that's important, but something that I would pay attention to is that down here, you have 1, 2, 3 peaks. Okay, you have 3 stretches, and you need to label all of those. You need to label that, this, and this. So all of these arrows, okay, all of these 6 green peaks that I've identified, you need to label. Everything else you ignore. Everything else you ignore. Okay, and so when I go down here and I look again, I look at my correlation table. Okay, I have 2 different types of carbonyl peaks. Probably I should pay attention to where an ester peak shows up versus a carboxylic acid. You see what I'm saying? And then the other one, again, look at what do I have? What functional groups do I have besides a carboxylic acid and an ester? Okay, I have carbon hydrogen. I have sp2 and I have sp3. I have carbon-carbon double bonding. I have the OH stretch, okay, of the carboxylic acid. So make sure you mention those. Okay, make sure you mention those. Okay. All right. Any questions? I promise this lab and the radical bromination are the 2 longest labs. Okay, in terms of, well, there's one, but anyways, it doesn't matter. By the time you get there, you'll have been sufficiently broken. Right, so it's all relative. Okay, no questions? All right, so what I am going to do, and I'm going to send an email out to the rest of the class, I'm going to push your lab reports back to where they're going to be due on Mondays. No, not Mondays. I'm going to make it Tuesdays. Your lab reports are going to be due on Tuesdays. The reason behind that is because of the online format, I'm working, a lot. I'm working a lot. And I want my weekends off. I was cleaning my house yesterday, and I was getting a whole bunch of emails. Okay, so this lab report is going to be due on the 29th. And so I need to have that way you can start working on the weekend and then start emailing me during the business day. And as you can see, on Tuesdays, I only have 1 class. I have something else going on, but for the most part, Tuesdays are my most free day, okay? Yeah, so there you go. You can still turn it in on Sunday. It doesn't matter. Turn it in whenever you'd like, okay? but you have to turn it in by the 29th. Okay. And so I'm going to go in and I'm going to adjust all of the due dates. And then that way, if you guys email me on a Sunday or a Saturday, you don't have to worry about me being outside mowing my lawn, because I know it's difficult sometimes to get it all done early and catch me during the week. So there you go. All right. Questions, comments, concerns? All righty, guys, I am done with you. I'm sure you're done with me. And then I want you guys to have a nice week. Okay. I'll talk to you later. Bye-bye.